Hi, I'm Galen Tunnicliffe, and I'll be presenting my work on Lab 2, the lines of charge. So for a little intro, this is based off of Lab 1, where we use Scotch tape, and we're trying to estimate the charge on each piece of tape to observe the transfer of electrons. Last lab, the tape was treated as a point charge in all calculations, but in this lab, we will increase the accuracy by treating the tape as many point charges instead of just one by dividing it up into little line segments. We assume that there's no air resistance. We also treat the charge on the tape now as many little charges along it instead of just one big one. And now we also assume that each U-tape we made had about the same amount of charge evenly distributed along the length of the tape. Some fundamental concepts. We need to know net F equals ma and that equal and opposite forces. We also need to know Coulomb's law, which is electric force equals K times Q times R hat over R squared. That's the electric force. And then we can modify that for the electric field by getting rid of one of the charges. We also need to know basic superposition and basic integration techniques. So to jump right into the code, this is a function that we'll use later to designate all the little point charges along our line or our piece of tape. So this is just a reference function that we were given that we'll use later. So right here is where we use it. For top and bottom tape, we use that function that was defined before. So what this does, it creates 30 little point charges or circles that you'll see in the diagram that we are integrating over, or that we separate for the charges to be distributed along. And if we continue with this, we see that the net electric force on the top tape is initialized at 0, just to start off the code. And then we have this big loop down here. This is for loop. So what this does is it creates an arrow representing the electric force from the bottom tape on the top tape at each of those 30 points based off of the electric fields of all of the 30 points on the bottom tape. So now we get to net electric force and gravitational force, which are going to be big arrows on the diagram. So the first big arrow is the electric force vector, which is the white arrow that goes up. And then the second big arrow is the gravitational force vector, which is the yellow vector that goes down. And then lastly, we have the printouts that describe the magnitude of the electric force and the magnitude of the gravitational force, which should be relatively equal to keep it levitating. So if you see now, you see all those green arrows represent the electric force on those tiny point charges, and then the big white one is the electric force on the tape, and then the big yellow one is the gravitational force on that tape. So results, the magnitude of the charge on one piece of tape for me was 2.04587 E negative 8 coulombs. If we had modeled each of the tapes as just a single point charge, it wouldn't be much different, but this approximation is slightly more accurate just because it's akin to real life more. It models real life better because we split it up into 30 line segments, which even though it's not infinity, it still models it better than just one point charge, because as we approach infinity, we get more and more accurate. Okay, that's my presentation, and thank you for listening.